Okay, so this is where we left off. We looked at intercooling, and in particular, we were looking at that chiller economizer. So if we go back a little bit, what we have here is a two-stage compressor, 1 and 2. And what we did was we took the discharge gas from compressor 1, and we took this intermediate pressure and temperature gas, and we mixed it together, which had an intercooling effect. But I think I also mentioned that this is a simplified diagram. Normally what we'll do is we'll take that intermediate pressure gas and flow it through the compressor motor, which is going to be usually like a semi-hermetic design. So we'll use that intermediate pressure gas to cool the motor, and then it goes and cools off the first stage gas, and then we compress a second stage gas. So we basically have two refrigerant circuits. One of them is this one here, which is like the intercooler circuit. So the gas comes from this intermediate economizer, which is kind of like an evaporator at intermediate pressure, right? So what we do is we have a pressure difference from high pressure to intermediate pressure. And in doing so, that flashes gas, so immediately some gas boils, and we use that cooler gas then, and we only compress in the second stage this flash gas. Or actually, what I should say is that the flash gas from the economizer only goes through the second stage of compression. And then kind of the other loop that we have is this other refrigerant circuit, which goes like all the way around. Okay? And so again, we've got a delta P, but because the delta P is smaller than the overall delta P from LP to high pressure, we end up getting less flash gas in the evaporator, better NRE. We've cooled the motor, and the intercooling effect has reduced the work that we've done in compression. So the number that they gave here, and I'm not too sure what the source of this was. I wish I had it. I don't think it's in your textbook. It might be in the textbook. A 4.5% efficiency increase using this economizer. And one of the terms that I think I use with you is what's going on here with this gas. We're taking the cool gas and we are going to cool off the superheated gas that's coming from the stage 1 compressor. And so really what we can say is we are desuperheating. Okay, and we know what desuperheaters are. So let's take a look then at this two-stage compressor system. And what I've done is taken the same thing under standard pressure and temperature conditions, okay, same as before. And the original one, we had plus 30 for the condenser, and we had minus 15 for the evaporator. And the original scenario was this sort of this light blue line where we've got across the expansion valve, we've got a big pressure drop that results in a lot of flash gas. In this case, it looks like it's about 15% flash gas and 85% liquid remaining. And then we compressed it. We achieved a really high temperature. I think it was like 110 degrees Celsius, something like that. Okay. And so we had adiabatic compression, which is problematic for us in terms of its energy consumption. And because we had lots of flash gas, we had a small net refrigerating effect. That was our NRE. So, you know, smaller NRE. And so then with intercooling, we took a look. Well, it's the same as the economizer. It's the same as this thing here. We've got intercooling going on in between stages of compression. So here we got two stages of compression, stage 1 here and stage 2 over here. And each one of these is adiabatic, so we've got adiabatic compression here, and then intercooling, and then adiabatic compression. So it's not true isothermal. I mean, a true isothermal line would be maybe more like that. Okay, but it's a jagged, and it's going to try and kind of mimic that isothermal compression. So we've increased the efficiency here by reducing the work done by each stage of compression. Okay, so this is reduces the work done per kilogram or per mass circulated per kilowatt of the evaporator. Okay, in other words, there's power savings. But then when we take a look at the other end of the chart here, instead of having one extreme pressure drop, now we've got two pressure drops. So we've got an intermediate pressure drop, and we've got another to the low pressure. And so we've got two delta P's going on here. And with those two delta P's, each step of expansion of the liquid results in less flash gas. So if this is our line of constant quality, and that's a 10% line, let's say that that's a 7% flash gas right there. Now what happens to that flash gas? Boop, 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 sucked in to the suction of the second stage compressor. That's where the flash gas is going. It's cooler. And what does it do? The flash gas mixes with the discharge from the first stage, and we end up over here. And so we end up with a cooler suction to the compressor and more efficient compression. That's what we see here. Where does the flash gas go? Into the second stage. So there's our intercooling going on right there. And then over this end here, because we're flashing off, what's left behind is saturated liquid. So that brings us back to this saturated liquid line. That's what's left after we flashed off that 7% of the gas. Now that goes through the second stage of expansion. And again, we're, I don't know, looks to me like it's about 7% flash gas in the evaporator. And now look what happens to our net refrigerating effect. We got a big increase in the net refrigerating effect so that we circulate less refrigerant per unit time to achieve the same evaporator tonnage, or the evaporator kilowatt. Okay, so we've increased the efficiency by affecting the net refrigerating effect, by intercooling to give us isothermal compression, and we've also improved the volumetric efficiency. So this is, I guess, here we go. Here's the next slide. So let's see what's going on here. Let's try and summarize the effects of multi-stage compression on a refrigeration plant. I should say multi-stage with intercooling. Now we know from reciprocating machines that we got a clearance volume, and the little clearance volume contains gas at high side pressure. And we know that that gas has to re-expand in the cylinder before the piston will actually draw in refrigerant from the evaporator. The greater the delta P across that piston from low side to high side, the greater the pressure of the gas in the clearance volume. Therefore, that gas has got to re-expand a pretty good distance, part of the stroke, before the piston can start to draw in refrigerant again. Okay? Just like with the air compressor, if we've got a smaller delta P across the cylinder, then that means that we get a lower pressure in the clearance volume, which means that it can expand to a pressure that's lower than the evaporator pressure with a shorter amount of the stroke of the piston. So what that means basically is we get a longer effective stroke, and we get greater volumetric efficiency. So by multi-stage compression, whether it's air compression or refrigeration compression, we increase the volumetric efficiency of our machines. That is a real bonus. Next, we saw how that changes the temperature of the discharge. So here, that's about 60 degrees Celsius discharge temperature. Or no, is that 60? Let's see. No, 45. That's 45 degrees Celsius here, following the lines of constant temperature. And if I follow this line of constant temperature, that's the 60 degrees Celsius. As opposed to 110, that's so much easier on our machinery. It's easier on the oil. The lube oil is more effective. The lube oil doesn't break down due to high temperature. Less wear and tear on the machine. So cool compressor operation is a much better thing. And what it also means is that it increases our condenser capacity. So for a given condenser size, if we go back here, that's how much heat we need to reject in the condenser per kilogram without multi-staging and intercooling. That's the amount that has to be rejected with intercooling and multi-staging. So that's equates to a reduction in the actual physical size of the condenser. And of course, we know about this. We looked at this already, the better compression efficiency, and we looked at the higher net refrigerating effect. So this applies to multi-stage compression systems. And do you need to know it? I would say yeah. Okay, you gotta know this stuff. Let's skip that. Now, okay, so this is one of the pictures that's in your Pan Global, and it's kind of complicated in its external appearance, but we're going to break it down into something that's less complicated. So, boy, oh boy, this is really old. So, for example, it's got these things here, which are called crossover valves. You don't need to know that those are crossover valves, and the reason you don't need to know it is because nobody anywhere installs crossover valves anymore. That's 1945 technology. And this picture here appears to be very 1945-ish to me. So for example, this here thing is the motor, and it looks like it's a big low-speed synchronous motor, and it's directly coupled to an HP compressor. Notice it's got a small cylinder and an LP compressor. And the LP compressor's got a big cylinder because it's going to handle vapor with a high specific volume, right? So or low density, if you want to say it that way. So let's see what's going on. What we have here is, lost the mouse again. So over here, what we have is our evaporator. And this sucker is operating at a very low pressure. And so here, let me just try and reboot my mouse. Very low pressure and low volume. I'll just turn that thing off for a while and try to use this one. Is this one going to move? No. Oh, okay. Look at that. I can see a mouse. Okay, so now what we're going to do is, so we've got warm brine comes in. So this is a flooded evaporator. It's a shell and tube heat exchanger. And now we're producing vapor. And that vapor is going to go through this suction line at low pressure, and it goes into our low pressure compressor. And the low pressure cylinder pumps it out into an intercooler, which is really, really interesting. The Pan Global gives you some wrong information. The Pan Global says this is no longer done. And I got to tell you, it is done. Direct liquid injection intercooling is maybe the most significant form of intercooling that is used in industrial ammonia refrigeration. It's very important. And I'll show you a picture of exactly what this looks like, okay? So what they're going to do is they're going to squirt liquid refrigerant directly into the discharge of that low pressure compressor, and they're going to intercool it because this gas is going to expand. Well, it's going to boil, right? It's going to boil and it's going to absorb superheat, which really means that this is a spray desuperheater. Okay, spray desuperheater, same like we see with the boiler, right? We want to desuperheat. When we go back here to this diagram, what are we doing over here? We are desuperheating. That's what's going on. And so the same thing is going on here in this diagram. We're actually spray desuperheating. What's the spray? It's not water, it's refrigerant. Where is it coming from? It's coming from the liquid receiver. Okay, so we've got some liquid goes this way, and it goes this way and into our spray desuperheater intercooler. Now, maybe we put a little bit too much in there, and so if we put too much in there, it's going to accumulate on the bottom, and you'll see where that goes shortly. We're actually going to grab that liquid at intermediate pressure. And by the way, again, this is now at intermediate pressure. So we're going to grab some intermediate pressure liquid that's overfed, and we're going to use it. Now, the next thing is from the intercooler, we've now cooled it off, and that's our suction into our HP compressor. The HP compressor is going to discharge out and into the condenser. And of course, we're going to have CW going in and out and turning it back to liquid, which flows then into the liquid receiver. So what else do we got going on here? So we've got a direct injection or spray intercooling going on here. Now we know that we want to decrease the amount of flash gas. By decreasing the amount of flash gas, we increase our net refrigerating effect. So when we condense here in the condenser, we might actually subcool a little bit in the condenser. Not a lot, but we could subcool it a little bit by 5 to 10 degrees. And then it goes into a liquid receiver, and the liquid receiver's got a particular level in it. And so the refrigerant's stagnant in there. It sits, I mean, it's always leaving, but it's also kind of sitting there for a period of time. So it does, in fact, radiate heat out into the room. So there's some subcooling going on in the liquid receiver, which is a good thing, but it's not good enough. We want to make it even more subcooled. So notice we've got warm liquid, which is still subcooled, coming from the liquid receiver, and we want to put it here into the evaporator. So what we're going to do is we're going to take it and we're going to put it through a heat exchanger. And so the tubes are going to go through there, and they're going to turn around, they're going to come out, and now we've got subcooled liquid, subcooleder liquid, more subcooled, cold. Okay, we've got cold liquid, and the cold liquid is going to go in, and now we're going to get very little flash gas, and we're going to have a big net refrigerating effect. But the question remains, how did we subcool that? Well, we put some refrigerant into it. Where did the refrigerant come from? The overfed intermediate pressure liquid from the intercooler. It's going to go la 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 la, as Dave Quintilio would say, la la la, through this pipe and we've got an expansion valve here. And so the liquid is going to go in here and it's going to boil away on the outside of these refrigerant lines that are inside. And then we're going to suck here into the HP cylinder suction line. All right, so in this way, we both increase our net refrigerating effect, and we have all of the beneficial effects of multi-stage intercooled type of system. Now, if you're having trouble following the diagram, I did put together this, and this is that. It really is. And I do have a description of this in the lecture notes. If you haven't seen the lecture notes, please check them out. But there's a full description of how this thing works in there. Again, this is third class. It's not a repeat of what was in your fourth. Any questions about this thing before we move on? Then what we're going to do is we're going to look at this rotary booster compressor deal, where we've got a two-stage refrigeration system, and this is a real low-pressure refrigeration system. By the way, this one here is probably a very low-pressure system too, because we're using two stages to compress it. If the delta P, in other words, if the evaporator pressure isn't too low, like let's say on a warmer temperature system, like let's say that instead of running that chiller at, say, instead of running the chiller at, say, minus 20 degrees Celsius, let's say that we ran the chiller at 0 degrees Celsius. In that situation, maybe we wouldn't need two stages of compression to get an efficient machine. Maybe it'd just simply be more economical to apply a single stage machine and not a two-stage machine. So here we're looking again with objective 5, another system that has got a very low pressure evaporator. And so what we're going to do is apply a booster to the very low pressure side. So really it's the same as what we just looked at, with the addition of, well, you'll see. We'll take a look at it. So here we got, in your Pan Global, it talks about using a rotary type of compressor. And we do know what rotary compressors are. And in fact, this is one right over here. Okay, this in fact is a rotary screw. It's a centrifugal compressor, or not a centrifugal compressor, it's a positive displacement compressor. And notice that the suction line, this is a very, very low pressure. I think that this is for like a minus 40 degree system. And you can see all the frost buildup. That's the suction line. So where the flange is exposed and uninsulated, lots of frost buildup. And then, what else are we looking at? Let's take a look at this business here. So if I look at the discharge side, so this is the compressor discharge right over here. And what do I have upstream of it? I've got a little isolation valve here. And then I got a liquid line, and I got a liquid line shutoff valve. And then I've got a thermostatic expansion valve, and I got another isolation valve, and then I've got a distributor. And what we're doing is we're taking liquid refrigerant, liquid ammonia, and we are injecting it directly into the discharge of the booster. So in other words, what we're doing is we are intercooling, or if we want to put it this way, it is a spray de-superheater. Okay, and that's where we're spraying it in. and then that's actually the discharge. And if we overfeed too much, like if we put too much liquid in there, we shouldn't because we've got a thermostatic expansion valve. But if we do put too much, the liquid will go into this vessel, which is like a separator vessel. So that takes us to this diagram, which is really very much the same as the previous one, but you can see this one here. We've got the addition of this sort of intermediate pressure evaporator. Okay, so let's take a look at how this one here is going to work. We'll start with the evaporator like we did before. Actually, what we have is two evaporators, but we're just going to start with this very low temperature evaporator. So this one here is operating at the lowest pressure. It's getting some liquid fed to it. Okay, so this is your liquid line here. That's the liquid line going in. And so it's boiling at very low pressure, very low temperature, and we're going to draw the vapor into the booster. And then what are we going to do? We're going to intercool it. Now, in this previous picture, what I show is a spray direct contact intercooler, like we saw here, okay, where we have an expansion valve and we spray it directly in. And then we've got this vessel downstream that separates. Okay, the vessel downstream that separates any overfeed. Okay, so that's one type of intercooler, but this is an intercooler that you might think of more with air compression, where we actually have got water, CW, going in, cool water, and going in and out. And so what we have here is basically a shell and tube heat exchanger, okay? So, in other words, we've got two varieties of intercoolers. One of them is the direct spray, which is a desuperheater, and then this one here would be more like a surface attemperator in a boiler. It's a shell and tube heat exchanger. And so the gas cools off before the second stage of compression. Now, then the next thing that it is going to do is we are going to actually cool it off a little bit more. And then it's going to get sucked into our second stage compressor. Okay, so this is LP gas. Okay, it's not intermediate pressure gas, it's LP gas. And so the second stage compressor doesn't simply take this gas here, it also sucks this gas here from the intermediate pressure and intermediate temperature evaporator. So again, we've got liquid going into that evaporator, gas coming out, gas now meeting up with the discharge gas from the first stage compressor. They meet together at this T-fitting, and it gets compressed to high side pressure into the condenser, CW in, CW out, and a liquid receiver with a gauge glass and all that kind of neat thing. All right, now let's take a look at, so we saw the intercooling, so we took a look at that volumetric efficiency end of things. We looked at the adiabatic versus isothermal end of things, and the volumetric efficiency increased by reducing the delta P across each compressor. Great. Now let's look at the net refrigerating effect end of things. We've got this subcooled liquid, which is still warm coming from the receiver, and we want to make it cooler. So what we're going to do is put it into a cooling coil. And then when it comes out, it's, sorry, I'm losing control. When it comes out of this liquid and gas cooler, they call it, it's now super duper subcooled liquid. So we're going to get much less flash going on in either of these evaporators. So what is cooling off that warm liquid? Well, some of the gas leaving the intercooler. And also what we're going to do is take, where is it, where is it, where is that little thingamajigger? Ah, there it is. That's what I was looking for. This little T here is going to take some of the subcooled liquid and put it through an expansion valve. And some of the subcooled liquid is going to go in here. And this black stuff here is actually oil, or not oil, it's refrigerant that's boiling away and getting sucked into intermediate pressure. Okay, so we are cooling the subcooling the refrigerant, the liquid refrigerant, using this cooler, which uses the combined effect of the cool gas leaving the intercooler, as well as it's fed with refrigerant directly. So in fact, it's kind of like an intercooler as well. Just a little bit more of a complex design. Now, if you have trouble following along with that, again, what I've done is I've taken it and drawn it out schematically. And again, there's a full description of that in your lecture notes. So just a little recap about what we achieve with these multi-stages: better volumetric efficiency, cooler operation, better compression efficiency, and higher net refrigerating effect, which ultimately all of these things combine to make a refrigeration plant more efficient. And when we talk about the efficiency of a refrigeration plant, we're really talking about the coefficient of performance. So in other words, how much energy is absorbed in the evaporators, okay, how much evaporative heat transfer occurs, which is the net refrigerating effect, and how much work is done in compressing it. And so if we increase the net refrigerating effect and we reduce the amount of work done, okay, then what we end up with is a higher coefficient of performance. And that's what we want. We want a high COP, which means we want to be able to transfer oodles of energy in the evaporator and compress it using a micro oodle of energy, if that's a unit. It is now. If you can have oodles and oodles, then why not have a micro oodle? I hope I'm not confusing you. I'm confusing myself at times. Oodles. So we can have oodles, oodles and oodles, and then I guess we can also have like a micro oodle. Again, COP is equal to our net refrigerating effect over our work done. And if we maximize the net refrigerating effect and minimize the work done, then we get a high COP, which makes us really happy. So next is describe and explain the operation of a multi-stage refrigeration system. We've done that. It reappears, Shazam. So objective 6 here, we've looked at it with objective 4, and frankly, we've looked at it with objective 5. The only difference this one here, we're not calling the low pressure compressor in this one here. We're not calling it a booster because the booster serves a certain part of a system. So here we have only one evaporator. If we had a second evaporator, so let's say we had an evaporator up here, okay, and let's say that that evaporator suction went only to here. Then what we would have is an intermediate pressure evaporator, which is what we saw on the previous system. Okay, but this doesn't exist in this particular one. If we had an intermediate pressure evaporator that fed only into the inlet of the second stage compression, then we would call this compressor down here, we would call it a booster. But we don't use the term if we don't have an intermediate pressure system combined with a low pressure system. So you can read more about that. We've basically covered it all. Okay, it's a little bit muddy in the third class, so hopefully I've cleared away some of the mud. Then the next thing is explain the components and operating principle of an ammonia absorption system. So with ammonia absorption system, what we have is some components that basically replace. Hang on a second. I'm going to reboot my my slideshow here because these problems are cramping my style here. Look at that, I got a mouse again. All right, let's start this thing up again. Okay, so I'm going to just draw this little compression refrigeration system. Here's our compressor, and the compressor is going to discharge into a condenser, and then we've got an expansion valve, and then we've got an evaporator. There you go. Now, we also have a high side and we've got a low side operating at different pressures and temperatures. Now, this is a compression refrigeration system. Why? Because we're using a compressor. But let's see if we can get rid of that compressor. And in order to get rid of the compressor, we've got to kind of identify what the compressor does. And so the first thing the compressor does is it sucks on the evaporator. So it removes refrigerant vapor as is produced from the evaporator, the rate at which the evaporator produces. So if we've got a high load, it's got to compensate for the high vapor production. If we've got a low load, it's got to compensate for the low vapor production. So the compressor is going to be designed for maximum load. And the second thing that it does is it increases the pressure and actually adds work. So really what it does is it increases the pressure and temperature of the refrigerant. Increases the pressure. And so why do we want to do that? Well, we've got a particular condensing medium. So this is our condenser here, and let's say we've got air going through at 20 degrees Celsius, with a fan over here, and it fans blow air through the condenser, which means that the temperature in here, inside the condenser, must be greater than 20 degrees Celsius. As a matter of fact, we saw that it could be easily 100 degrees Celsius or so. But the bottom line is we must increase the pressure of the refrigerant so that it has a temperature that is higher than the condensing medium that's available, and therefore so we can convert it back to its liquid form so it can be reused in the system. So we need to increase the pressure and temperature of the refrigerant. It's another thing that the compressor does, and it does that by adding work. So the work done. Now, if we're going to replace this compressor with other components, what are we going to do for number one here? Well, for number one, we are going to have to have something that sucks the refrigerant out, and that is called the absorber. Now, the absorber is a vessel. It's a pressure vessel. And it's full of something that has got an amazing affinity for ammonia. And it will suck the ammonia out of the evaporator like nobody's business. And that material is water. And the water actually has to be cool, because we know of the solubility of gases in liquids. And we know that the solubility of gases and liquids is a negative solubility curve. So that as the temperature of the water goes up, the solubility of the gas goes down. So at low temperature, this stuff will suck lots and lots and lots of ammonia vapor. But at high temperature, it doesn't. Actually, at high temperature, it's like a deaerator in a steam plant. We heat it up, we heat up the water, and it gives off dissolved gases, right? Well, same thing here. We're going to heat up that water, and it will release the dissolved ammonia. But that's done by another component. So the first component is going to suck the refrigerant out. Now then the second function we said was increase the pressure. We'll call this 2A, okay? 2A is increase the pressure. What are we going to use? A pump. There you go. So we're going to take the liquid from the absorber and we're going to install a pump, and the pump is going to take things from low side, so the absorber is at low side pressure, and we're going to pump it up to high side pressure. But then we're just going to have high pressure liquid, and we've got to do something about it. So that takes us to 2B, and so 2B is what we call the generator, where we're going to take this water that's got lots and lots of dissolved ammonia in it. We're going to heat it up. So this is a pressure vessel. It's at high side pressure. And maybe what we'll do is we'll put a steam coil in it. Okay, that's one option. Or what we can do is have direct fire. So we can put a little fire in there and have flame safeguards and all this boilery type of ignition, pilot trough for ignition, all that kind of stuff, purging, blah, blah, blah. Lots of different heat sources. All we need is heat. And so this liquid that we put into here, we're going to heat it up and we're going to drive off ammonia at high pressure. So what have we done then? In this system here, we are going to replace the compressor with these three components. So with number one, the absorber. Number two, the pump. And number three, the generator. And so let's take a look at these systems. Now this is the super complicated one that is in your Pan Global, but let's start off with one that's less complicated, simplified one. So what we have here is a generator. And let's start with, I like starting with the evaporator, okay? Maybe we'll start with the expansion valve. So here's our metering device. Now, maybe it's low side float, okay? Because this is likely a shell and tube heat exchanger. And what we've got, chilled water. So we're gonna have a chilled water pump, you know, and or brine, or whatever it happens to be. If it's an industrial refrigeration system, you know, maybe it'll be a brine that we're chilling off to -30 or something like that. Anyway, in the evaporator, we've got R717, and that R717 is boiling under low pressure and low temperature. And the vapor, and cooling off the chilled water, of course. The vapor then gets sucked by the absorber. It can't help itself because the absorber has got cool water in it, and the cool water has a huge affinity for the ammonia, and so it's just dissolving it like crazy, which is maintaining the low pressure in the evaporator. Then what we're going to do is we are going to pump it. And so what we have here is our dividing line between our high side of the system and the low side of the system, okay? So after the pump, we're now on the high side, and we are going to take this stuff that is, well, we're going to call this stuff aqua, Okay, and this stuff here, because it's got uh, a lot of ammonia in it, we're going to call that strong aqua. Okay, so that's our strong aqua. And after a while, it doesn't want to dissolve anymore. Plus, it's full of ammonia, and we want to put the ammonia back into the system. So we pump it into the generator. We apply heat, in this case with a burner. And what do? We drive off ammonia gas. The ammonia gas then goes into the condenser, and maybe we got a liquid receiver. I don't know. And then again back through the metering device. So that completes our cycle. But we can't just continually pump strong aqua into the generator. It's going to fill up and overflow and whatever. We got to basically take this aqua that's in here. After we drive off the ammonia, it becomes what we call weak aqua. Well, weak aqua is a really good thing because that's the cool water here. This cool water in the absorber is actually what we're going to call weak aqua. That's what goes in there, but it turns into strong aqua as it absorbs NH3. But somehow this weak aqua, the stuff that was started off as strong aqua and then became weak aqua, we got to get it back into the absorber. Now, I don't like the way that this image presents it. What we should have is sort of a pipe inside, and that pipe delivers, because we've got a delta P here from low side to high side, it will automatically flow according to the pressure gradient, and it's going to spray into the absorber. And by spraying into the absorber, we got a large surface area, so it really helps suck the ammonia from the evaporator. But we've got a little bit of a problem here because we've got a burner here. This stuff here is hot. And we said that hot water doesn't absorb ammonia. We want it to be cold water inside here so it has an affinity. So we got cold stuff going into the pump, and we got hot stuff coming back, and that's lousy. Because if we got really cold stuff going in, that means I need more fire and I need more energy or steam flow or whatever it is. I need more heat input because what was going in was cold. Boy, if we could only preheat it before it goes into the generator. Now, this stuff here, the weak aqua going back is hot. And that sucks because it's not going to absorb much ammonia while it's hot. We want it to be cold. I know what to do. Let's make a heat exchanger. And the heat exchanger is going to be like this. So what we end up with is hot, weak aqua comes into the heat exchanger and is cooled off by the cold, strong aqua, leaving the absorber, resulting in nice, cool, weak aqua that's going to absorb lots and lots of ammonia as it sprays into the absorber. And we got this cold, strong aqua, and it's going to go through here. And it's going, oh, look at that! I'm going to heat up, and now we get hot, strong aqua going into the generator, which means that I can turn down the fire. I don't need as much heat now, and my system is a more effective refrigerating system. And on top of it, we're burning less fuel, so we get better energy efficiency. Now, I think it's break time. let's just quickly look at this here. I'm not going to go over the description, but this diagram here is a little bit more complicated than what we just looked at, but all the principles are there. In this case, they're using steam as the heat source for the generator. So you see there are steam coils, and we're going to have a steam trap there and condensate. Now, one of the things that's going on here is this analyzer. And so from the heat exchanger, we've got this hot, strong aqua is going to go in there, and it's actually going to absorb moisture. So we said that in the generator, there's NH3 and water, and the water is what I'm calling moisture. And so by spraying it into the analyzer, it kind of causes any of the moisture that might be entrained in the high pressure vapor, it causes that moisture to go back into the generator. Okay, so we want to recover the water. We don't want the water to go into the condenser. We want the water to stay in the generator and then go back as weak aqua into the absorber. Now the second stage of that moisture recovery is this thing here called the rectifier. So what we're going to do is put CW in, so cooling water through a coil, and if any moisture is still in there, well, we're going to condense that, and it's going to drip back into the analyzer and into the generator. So the whole idea is for these things here, they basically dry out the refrigerant. And we know that we want our refrigerant to be dry because if we've got moisture in the system, it can freeze in the evaporator, causing blockage, or it can freeze at the metering device and obstruct the flow of refrigerant. So we don't want moisture in it. So the rectifier and the analyzer are working together to help dry out the ammonia vapor. And then we got a condenser, and we got CW and the liquid going into the evaporator and blah. So it's all the same kind of stuff. The only thing to point out on this particular drawing is it's got that heat exchanger that I showed you, but it also has this additional analyzer and rectifier that are just there to dry out the vapor. So, time for a 10-minute break. We'll see you back at 1:08. Okay, back 1:08. And I'll stick around for a couple of minutes during the bio break here if anybody has any questions about what I just went over. well. Just 2 minutes left. Well, some of you might not be back yet, so I'll wait a little bit. But I just wanted to show you this picture. We're not going to go over it, but it's the same thing that we just looked at before, but a bunch of things are being housed in a single pressure vessel. And that's kind of how things are with these systems. Well, actually, what we see is the absorber and the evaporator are in the same vessel, and with some drift eliminators in between them. This is going to be in your handouts. You can look it over. This is from modern refrigeration, but just to give you an idea about how these things are configured. Obviously, we don't have these, discrete pieces of equipment that act as functional blocks. Engineers have, put these things all together into something that kind of has a flow like this, and that's basically how these chillers are going. Now, of course, there is also the lithium bromide system that's used in HVAC. We've been talking industrial ammonia refrigeration, but we do see things like this in HVAC, but instead of water being the absorbing medium, the absorber is full of lithium bromide solution, and water, in fact, would be the refrigerant boiling under a very deep vacuum. And you hopefully you had an opportunity to see the lithium bromide absorption chiller in the SAIT powerhouse. It uses steam coils as a heat source, and there you go. You can research it. You can see what they actually look like. Some interesting stuff. There are a number of manufacturers for industrial ammonia absorption systems. Okay, that's it for chapter 10, which leads us to chapter 11. And chapter 11, I think, is again, it's a little bit problematic because there's just so much stuff in there that is rehash from the fourth class. And I can pull it out right now, and I could itemize over and over again. What have we seen already in the fourth? What have we seen? And it'd be a shorter list, a much shorter list to say what's new in chapter 11. So, for example, chapter 11 talks about oil stills. And in the fourth class, we talk about oil pots and about draining oil pots and what does an oil pot do and how do we get oil back into the compressor. But so third class has this thing called an oil still, and frankly, I don't even know if oil stills are used anymore. But it is in your third class, and I think we'll cover that next week. We'll do oil stills. Now, I also know that there's purging that's covered in your third class, and I think that it's also covered in your fourth class. The whole idea of getting rid of non-condensables from the system. Now, with a steam system, we want to get rid of non-condensables. Why? Because the non-condensables are corrosive gases. They're CO2 and they're O2. And so what do? We go to the deaerator. We mechanically deaerate it. So in other words, we heat up the water. And so these gases are insoluble. So if you think about it, it's kind of like a generator, isn't it? It's like a generator where we are applying heat to water and we're driving off dissolved gases. Now, how do we know that the deaerator is working? We look at pressure and temperature relationship, and we see that the pressure in the vessel equals the saturation pressure at temperature, the temperature of the saturated water in the deaerator. And we go, oh, Yeah, they agree. The aerator's working. But when the deaerator pressure is considerably greater than the saturation pressure of the saturated water in the storage tank of the deaerator, we go, oh, we've got too much pressure, our deaerator's not working. And again, our concern about a deaerator not working is dissolved corrosive gases. We call them non-condensables, but frankly, we don't really care too much about the fact that they don't condense. We care that they are corrosive dissolved gases, and we don't want them in our system because they're going to eat away at our boilers, they're going to eat away at our feed water piping, and on and on and on. Okay, that's our big concern with non-condensables in a steam plant. In a refrigeration plant, though, we've got non-condensables, and we don't care that they're corrosive gases or this or that. Frankly, it's not going to happen in our system. What we care about is where those non-condensable gases go. And where do they go? They go to the high side of the system. They get pumped by the compressor and they accumulate on the top of the condenser. They accumulate at the top of the liquid receiver, and they occupy space, and we've got a pressure on the high side that is greater than the saturation pressure of the high side liquid. That's how we know. Our high side pressure is too high, but we look at the high side temperature, and the high side temperature looks just fine. The pressure is too high, which means that our compressors are working harder and they're consuming more energy to get the refrigerant from low side pressure to high side pressure. That's one of the problems. Now, also we could have a high side pressure that exceeds the maximum design pressure and start popping safety valves. We don't like that. We can get a high side pressure that trips the machinery off before the safety valves pop. So we got high pressure cutoffs on the system. We don't like that. We don't want our system tripping off. And also the non-condensable gases in the refrigeration system occupy volume, occupy heat transfer surface area in the condenser, and basically reduce the overall capacity of the condenser. So we're trying to get rid of non-condensable gases. And so the fourth class talks about purgers, and the third class also talks about purgers as well. But I think that's one of the topics that we are going to revisit because purgers are a pretty important little bits of information.